let's take a look at this graph right here. Now, I've left off the title and the figure label on purpose because I want to help you to train your brain. If you're going to be an athlete, you have to train your muscles, right? If you're going to be a chemist, you've got to train your brain. No, you don't have to memorize this. Okay? But I want you to look at those chemicals listed over on the right-hand side. Okay? What can we figure out just by looking at the formulas within these temperatures is listed here from 0 to 100 degrees C? What physical state would those be in their pure form? You think they're all solids? How do you know that? How do you know they're solids? NaCl is a solid. What about the rest of them? What class of chemical? Because in the last unit, we looked at classes of chemicals and their boiling temperatures and freezing temperatures, right? Okay. So NaCl is what class in those 5 classes we looked at in the last unit? We looked at polar covalent, nonpolar covalent, ionic, metals, covalent network. Which one of those 5 classes does NaCl fall into? Ionic. How do you know that? Metal and non-metal combination. Okay. Can you see any other metal non-metal combination there in that list? CaCl2. That's also ionic, metal non-metal. KBr, metal non-metal. Well, lithium sulfate, the third from the bottom, that's not. It is metal and non-metal, but not a single metal and single non-metal. The difference there is, well, there's potassium sulfate too. What of those 5 compound classifications do those 2 fit into? This goes back to Unit 3. Polyatomic ion, so what does that tell you about the type of compound? It's ionic. If the formula contains a polyatomic ion, it must be an ionic compound, right? At least in a simple ionic compound. So, all the metal, non-metal combinations are ionic. All those combinations that have polyatomic ions are ionic, right? And all of those would tend to be what physical state in their pure form at room temperature and pressure? Solid. Are there any other compounds then in that list that are not ionic?
What's the chemical form of sucrose?
Well, is sucrose then ionic? What is it?
What's the chemical?
We just used it yesterday.
Oh.
What is sucrose? It is not. It's not a simple sugar. What's the form? What do you call table sugar? Sucrose. No, but what physical state would sucrose be in at room temperature and pressure in its pure form?
Solid.
You saw it yesterday. You should know. Solid, right?
Yes.
All right. How about the last chemical on there? Well, no, potassium sulfate we said was going to be a solid because it's ionic.
Yeah, but you said the last one.
No, I'm talking about the last one that we haven't covered yet. Glucose is the only one left. What physical state is glucose going to be in at room temperatures and pressures? Solid. Sugars tend to be solids at room temperature and pressure. Okay? Whether they're simple or complex, they tend to be solids. All right. So we got a whole bunch of solids here. All right? If I just gave you that list, you should be able to figure out, using this process we just went through, this process I just described, figure out what physical state they'd be. Okay, you can look at them and say, oh, from those formulas, those are all solids, because they're all ionic or they're sugars, right? And sugars and ionic compounds all tend to be what physical state at room temperature and pressure? Solids. Okay, now, so what we're looking at then is the dissolving of solids in. Look at the graph. What? In water, because it says on the vertical axis the amount of the solubility of something in grams and 100 grams of H2O, which is water. Okay, so we're dissolving something in water and we're increasing the temperature. So what can we learn about the solubility of solids as we increase the temperature, at least when we're dissolving them in water? Solubility goes up with temperature.
In some cases.
Is there any of them going down?
Yellow?
No.
The yellow one does go down a little bit after it goes up a little bit, right?
Yeah.
What about that?
The green one does down there near the bottom a little bit. Okay, but most of them go up, right?
Yeah.
All right. So as a general rule, not absolute, can't always depend on it, but most of the time you can assume when you increase the temperature of water, what do you do to the solubility of a solid? Increase. Does that make sense? That's not hard, is it? Not when you figure out those are solids. All right. Let's take a look at these. All right. What would the physical state of these chemicals be? They're all gases?
Yes.
All right. Yes, he says. Anybody doesn't know or disagree? Okay. How do we know that CH4 is a gas?
Oh, because it's below the.
Chain length is 5 carbons or less in a hydrocarbon. Right. Good. All right. O2. How do you know it's a gas?
O2 is one of those gases that you told us to remember.
Okay. It's one of those I told you to remember. Also, you're breathing it, so it's got to be a gas. How about carbon monoxide? CO. It's a poisonous gas. You should know that one. It's just kind of something you should know. All right. How about HE? Helium is a noble gas. Less dense than oxygen. All right, good. So these are all gases. Well, what's happening to the solubility of these? Now, I couldn't find a graph I could grab hold of in a hurry off the internet that was used the same units of grams dissolved in grams, but it basically works out the same way. Okay, so this is the solubility of gases in water. What can we say about the solubility of gases in water as you increase temperature? Decreases. All right, so gases tend to decrease their solubility as you increase temperature. Solids tend to increase solubility as you decrease temperature. Okay? So, what part of the ocean would have the most dissolved oxygen?
Arctic?
The Arctics, sure.
Very bottom of the Arctic.
Oh, the very bottom of the Arctic, maybe. Okay. Well, you know where they get the most fish out of the ocean?
The very bottom of the Arctic.
The colder places. That's where the most fish live. Huh? Not less salt, just more oxygen. They fish for cod in the North Atlantic because that's where they are, where there's more oxygen. Okay, you can tell the kind of conditions that fish need to survive by the conditions of the water. Okay, where do you find trout? Anybody a fisherman in here? Where do you find trout in fresh water anyway? Nobody knows?
Streams.
What kind of streams?
Freshwater.
What does this mean? Somebody's doing a sign language thing up there, back there. Okay? He's saying that upward. He's doing, all right, that's off the screen here. All right. I'm sorry. I'm recording this so people can't tell he's doing this. Okay. All right. Let's go back to mine.
Upward streams.
Upward screens. Okay. So, high up in the mountains, or at least in the higher Piedmont anyway. Okay. Colder streams. Also, the water's running faster, dissolving more oxygen. That's where you find trout. In freshwater, trout anyway. Okay? They need more oxygen.
Wait, so if it's less soluble, then there's more of it, like more oxygen?
If it's colder, you can get more oxygen dissolved. If it's colder, you have more oxygen dissolved in the water usually. Okay? And in mountain streams, that's where you find the trout. Okay? Where do you find bass?
Salt water.
Well, you do find bass and trout in salt water. There's saltwater bass and saltwater trout. Okay, well, let's talk about freshwater. Where do you find bass?
At the bottom of the mountain.
At the bottom.
They don't live in mountain streams.
They live in the bottom. Like
Man, you guys need to get a fishing pole, you
Oh,
know?
I'm sorry, we don't fish up.
I know. I'm telling you.
One time I ain't catch anything.
Bass live in, yeah, you can find some bass in rivers, but mostly you find them in lakes.
Ponds and lakes.
You don't need as much oxygen for a bass as you do for a trout. Okay? How about catfish?
Oh,
Oh,
catfish
shit.
are, they're in
Fresh,
lakes
muddy, salt
too.
water.
You can find catfish in almost any kind of water if there's almost any kind of oxygen in there. They'll live in ponds. They'll live in swamps. They'll live in brackish water. They'll live everywhere. Okay?
Do they eat people? Is it true that they eat people?
Catfish? I don't know. Let's go get into catfish eating people. Let's talk about this. All right. Yeah, it's called, what do they call that when you stick your hand in there?
Wow.
It's not gigging. Yeah. What do you call it? Noodling, that's right. All right, now, let's go back to this. Listen, catfish don't need even need as much oxygen as bass or trout. And if you have a place in a stream or a river where there aren't any catfish and no trout and no bass, and maybe you got some little creepy crawlers in there living in there, well, that probably has a whole lot less oxygen. Okay? And if you have a little stream in a hot place in the woods and there's a lot of trees that have fallen down in that stream, like in a swamp sometimes, okay, you won't find any fish. You'll find little creepy crawlers. Okay? Crayfish, crawdads, little worms that live down there, things like that. Okay? So you can tell the health of a stream by the creatures that live there sometimes. Okay? All right.
Isn't like the sun like healthy like areas that have frogs?
Well, frogs can live where there isn't as much oxygen because they don't really breathe oxygen in the water unless they're tadpoles. And the tadpoles don't need as much oxygen as do fish. So it would depend. They need more oxygen than some of the creepy crawlers, okay, but they don't need as much as fish, okay. But of course, once they become adults, then they breathe air out of they're amphibians. So they start out with gills and end up with lungs. Okay? All right. But that's another story. All right. So if you want to increase the solubility for a salt, you usually heat them up. If you want to increase the solubility for a gas, you usually decrease the temperature, right? All right, here's a question that's practical for you. Okay? You open up a soft drink. Is it going to stay carbonated longer in the fridge or the counter?
Fridge.
Why?
Because it slows down the particles, so they're not trying to escape as quickly.
Look at this graph.
I did it.
Look at the graph. Is it going to hold more CO2 when it's in the refrigerator or on the kitchen counter?
It's in the refrigerator.
Why?
Freezer.
Because it's colder. Well, if you freeze it, that's a whole different thing. Okay? It actually drives out the CO2 when you freeze it.
Yeah, and then whenever you thaw it out.
All right. All right, you get that? That's an important thing for you to know. That you increase solubility of salt usually when you when you heat up the temperatures of the liquid solute like water, and you decrease the solubility of a gas when you heat it up. Now, here's another question for you. Think about this. Summertime, deep part, July, hot, early August, have a drought. We got a drought, okay? Not a lot of rain falling, not a lot of water flowing through the streams, okay? What's going to happen to some of the fish in those ponds?
They're going to die.
Why?
Because they don't have much
There's less oxygen.
Oxygen's less dissolved. No streams, water's not running through there to stir up the oxygen, get it dissolved. Yeah, you're right. You're gonna have fish dying. Get fish kills. Okay. All right. Now let's talk about dissolving things in water because that's our most common solvent. Besides heating up the temperature, let's say I've got a solid I want to dissolve in water. I want to increase the rate at which I can dissolve it. I want to dissolve it in a hurry. Okay, let's just take sugar. We dissolved sugar yesterday. All right, I could heat it up, but let's say we're not going to heat it up. How else can I increase the rate at which I can dissolve the sugar? Stir it. How else? Shake it. How else? Less of it. Let's keep the amount the same.
Less concentrated.
We already talked about heated up. Less concentrated means less of it. So, how else can I speed up how fast I can dissolve the sugar? Breathe into it, he says. Nah.
Yeah.
That's not good. Okay, let's talk about solvation. Remember solvation. Okay? What happens with the water molecules when they solvate a solid particle?
They split apart.
Okay, so they have to get around and surround that.
Like,
All right.
match up with it.
How do you get something so you can get more water molecules surrounding more particles of the solute more quickly? Huh?
Yeah.
More how would you get more surface area?
Smaller.
Smaller particles. What does that mean?
Crush up the.
Crush it up. Okay?
Is that more like Splenda? It's all like easier than.
I don't know. Splenda is just a different chemical formula. All right. You ever heard of a mortar and pestle?
Yes.
You know what they use them for?
Yes, you use it to grind up pills and stuff.
Okay, so they will dissolve faster. That's what a mortar and pestle is used for. Okay? So if you want,
Use it for guacamole, too.
huh? Use it for guacamole, that's right.